The atomic nucleus consists of protons and neutrons. The combination of the number of protons and neutrons makes a rich variety of nuclei. But physicists know only one-third of them. Uncultivated region is very interesting, but we could not see any of them in the laboratory so far. We, Center for Nuclear Study, are developing the opportunity to study what is the essential physics in the nuclei. Here is the world's highest intensity of exotic nuclear beam, the rare isotope beam factory. So we make a rich opportunity to study the exotic nuclei.
Neutron is moving in the nucleus around 20% of the speed of light. To know this is the property of the nucleon inside the nucleus, we need a beam of the same speed. This device called OEDO is such a device, and we also developing germanium detector array named GRAPE, so we can measure the gamma ray energy with few keV energy resolution. The super heavy element will decay a few milliseconds, but close to this super heavy element region, it is predicted there is a stable nucleus. We want to challenge to make this stable nucleus.
We can discuss the shape of nucleus and its dynamic properties like rotation or vibration. Nucleus of daily surroundings is in the frozen state, so we have to excite the nucleus by using nuclear scattering. We have a magnetic spectrometer, Charac, among the first magnetic spectrometers, which is dedicated to scattering measurements by using the RI beams. We can say something about inner side of the neutron star by studying neutron-rich nucleus produced by RI beam factory.
In nuclear theory, the main issue is to understand the exotic structure of neutron-rich nuclei. We study nuclear structure calculations in which we follow the motion of protons and neutrons inside the nucleus. But nuclear force is quite complicated. We solve the quantum many-body problem of the protons and the neutrons fully by using supercomputer. Still, even now, nuclear theory cannot provide us enough accuracy for the purpose of engineering. We would like to improve accuracy.
We know the basic story, how the elements were created in this universe, but we don't know the details, and there are still many mysteries. The facility we are currently using is called CRIV. This facility can produce low-energy RI beams. It's very good because astrophysical reactions take place at quite low energy compared to the typical accelerator energy. At the very beginning of the universe, the first nuclear synthesis produces the lightest elements, hydrogen, helium, and lithium. But we don't know how much lithium can be produced from the hydrogen or helium very precisely. So we want to solve this problem.
Shortly after the Big Bang, temperature was around 2,000 billion degrees. In such high temperature conditions, hadrons melt into a soup of quarks and gluons. And this is a new state of matter called as quark-gluon plasma. So high-energy heavy ion collisions are only the experimental ways to create a quark-gluon plasma. Our CNS participates in two big international collaborations, the Phoenix experiment at the relativistic heavy ion collider and the ALICE experiment at the Large Hadron Collider. Many measurements we did so far showed that the quark-gluon plasma made by us behaves like a liquid, not like a gas, and is the most strongly interacting system in the world.
We are searching for the evidence for matter-antimatter asymmetry in the present universe. so-called CP violations. In particular, we will search the permanent electric dipole moment, EDM, of elementary particles, which is the important observers of the CP violation. The signal of the CP violation is very small, so we want to realize a very stable environment. We make a lattice potential using a laser, and we put the atom one by one into this potential. Then we can measure the EDM very accurately. We will study the origin of the violation of the fundamental symmetry. We want to attack the mystery of the creation of the matter-dominant universe.
Deepening the knowledge of each subject is important, but the communication among each field aims at universality in the hierarchy of matter in the universe.